So, hi and welcome everybody to the Introduction to Communication Principles. In today's lecture, we will talk about information representation, communication system block diagrams, the basic one and the advanced one, and we will discuss the difference between analog and digital systems and give examples on each. And then we will study some of the performance metrics that are used in communication system to evaluate the performance of your modulation scheme or your coding or whatever methodology you have used to transmit your data. And then we will study the data rate limits that was defined by Shannon. So the major classification of data can be text, can be image, can be video, and at the end of the day, in a computerized system, all these different types of information can be represented in bits. So at the end of the day, data can be classified into analog or digital. Analog signal, if I ask you to give me examples on analog signals, you tell me speech is analog, music is analog, temperature reading, images stored on film. Anything that's continuous, that takes infinity number of values within a certain duration or between two different points, then this is analog. However, if you have finite set of values during a certain duration, then you have what's called discrete or digital system. Analog signals can be represented approximately using bits. For example, I told you in the previous lecture, when you want to record your voice, you just open the recorder and you start talking. What are you talking is analog. And the recorder takes your analog signal and it tries to convert it to bits. But how does it do that? Through sampling, quantization, and then convert it to bits. And depends on the number of bits used to represent each level of your voice, the quality of the recording will be higher or lower. If the number of bits used to record each bit is high, let's say 8 bits per sample, then the quality of your voice will be good. If it is lower than this, then the quality of your voice will not that be enough. So you have digitized images, digitized videos. All of them are kind of different representations of your analog signal. Bits are produced by computers, whether the source of data, picture, image, video, any kind of these types are all at the end of the day converted to bits. And then at the physical layer, you try to send these bits by changing the properties of a carrier that can pass through cables, through the wireless, through the medium, through fiber optics, whatever. For example, if 0 comes, make the signal +5, give the signal amplitude of +5 volt. This is if 1 comes. If 0 comes, don't send anything. Make the level of your signal 0. This is how you can communicate. The receiver then receives the signal. If it is at the bottom 0, the level, what does it mean? You have transmitted 0. If it is +5 volt, this means you have transmitted 1, bit 1. And by doing so, you can convert your electrical signal to bits. Analog signals can be converted into bits by quantizing or digitizing. Early analog communication, example on these, telephone, phonograph, film, sound tracking. Key to analog communication is the amplifier. We always in analog communication system, we always use amplifiers in order to increase the amplitude level of your signal. When you increase the amplitude level of your signal, what happens? You can reach farther distance. So your communication range increases when you increase the power of your signal. For example, when you talk in a loud voice, your friend who's 1 kilometer far from you can hear you, maybe. But if when you talk in very low quality, in a weak voice, like just whispering in the ear of your friends, he barely can hear you. Yes? Broadcast television was analog also until 2009, and then it becomes the digital TV. Early long distance communication. Now, having talked about analog and gave you examples on analog, what are the examples on digital communication? In the old days, we used analog communication. How did we use it? White flag, smoke signals, bugle calls, telegraph, they were all digital, almost. Why? Because there is finite set of values you can produce, finite set of things you can choose to send your information. For example, white flag, it's like 0 or 1. When you achieve victory or you win the battle, you raise, let's say, green flag. Then people who sees you, the people who see you from, let's say, 10 kilometers away, they know that you have won the war and now you are relaxed. You don't need any help. But if you raise the white flag, then they see that you are in trouble and they need your help. So you go and help them. This is kind of communication. Did they talk to you? Did you hear them? No, you just see the flag. This two different things you are using, we call it digital system. Why? Because how many different values you can choose? 2. It's finite, means you can count them, limited. Teletypewriter is also another example of digital system. Fax machines as well, and Ethernet and the internet. As you know, fax machines, nobody is using them anymore. They are very old and people are using scanners and telephones instead of them, phones and mobile phones. So now what's the structure, the basic structure of communication system? The most fundamental basic one can be described in the picture you see in front of you. Basically, you have your input message, which is here. Your input message passes through transducer. What's the transducer? It's like, let's say, microphone. Anybody knows that example on transducer is the microphone. The microphone in your mobile phone, the microphone when you talk to the public. What does it do? It takes your analog signal, the speech signal, and convert it to electrical signal. Once it's electrical signal, these electronic devices can deal with your signal, can manipulate it, improve it, encode it, encrypt it, modulate. You understand me? It becomes understandable to your computer. So your input message, let's say your speech, goes through transducer, which is the microphone. Your analog signal here becomes what? Becomes electrical signal. Then the electrical signal is still, it's kind of analog here as well. It's not yet sampled or quantized. So what do? You have a transmitter here. But this transmitter has like analog to digital converter. It has modulation, encryption, decrypt. It has encryption, encoding, interleaving, amplifier, filters. All these are many blocks are embedded inside this simple one transmitter. But for simplicity, right now we are showing you only the transmitter. But there are many things. Each block within this block is a course by itself. We can give a course within each block. And then the output of this is the signal that's ready to be transmitted over the media. Now you have prepared the signal in a good form, in a good shape that's suitable to be transmitted over the communication medium, whether it's fiber, copper, wireless, whatever. And then you have the channel. This is the medium, the channel I'm talking about. The cable, the Ethernet cable, the fiber, the air, the wireless, the microwave, whatever. This is the channel. is the medium that your data goes through it. Understand me? So the medium is responsible for conveying your information, kind of. But also it adds impairments, means some difficulties to your reception. It can add noise, it can add fading, interference, and many other problems that you need to tackle at the receiver and deal with. You have the receiver, the main goal of the receiver is to be able to extract the transmitted information from the noisy received signal. The receiver receives a signal that's full of noise, full of corruption and impairments affected by the channel, because when you send your signal, it hits the wall, it hits the trees, it hits the ceilings, it comes out of many reflections and finally reaches your phone. So the signals are confused. How can your receiver recognize your data? He needs to adopt and use complex, very sophisticated detection algorithm to be able to extract the net data bits that you transmitted initially at the transmitter. And then you convert your data bits back to analog signal so that your ear can hear the voice or your eye can see the picture or video or whatever. Basically, your eye and ear deals with analog signals. Yes, computer deals with digital. Analog is something natural, usually. Digital is something artificial. And why analog is very costly and difficult to deal with. That's why we go to digital, simplifies things. So also this block diagram includes the source encoder that converts messages into message bits, transmitter convert message signals into format appropriate for channel. I already mentioned all these ones while I'm explaining the block diagram, but you need to, if you want to understand more about these things, you can go to the book that we are considering. Now the first one is basic. This we call it the most basic communication system that everybody needs to be knowledgeable of. If I ask you in the exam or anybody tells you, explain to me what's communication is all about, you tell him you have transmitter, you have channel, you have receiver. And at the transmitter you have your data, which is in analog format. You convert it, try to convert it to bits, and then you try to prepare the bits in a waveform or in a shape that is suitable to be transmitted over the air. And the receiver job is to receive the signal that's corrupted by many impairments and many drawbacks caused by the channel and get back your original data bits. So this is the basic. But when he asks you, but what is the transmitter really is? What's there in it? You tell him you have there are many main functionalities in the transmitter. The first one, source encoder, which we explained it previously, takes your data, compresses it, and then if you have 1,000 bits, you produce how many out at the output of the source encoder? Let's say 500. So your data means the size of your data becomes less. Since it becomes less, you need less memory. And that's very useful, yes? And we like it because you save resources. And then you have encryption. Why do we have encryption? To protect your data from malicious users, from eavesdroppers. And then you have channel encoder. Why do we have channel encoder? To protect your data from the noise. And what does it do? It just adds redundancy to your data. So instead, let's say the input of the channel encoder is 100 bits, the output will be something like 200 bits. So what happens? You increases the size of your data. But why? We said that we don't want to increase the size, we want to save memory. But here we want to protect the data. Because we want to protect the data, we lost some memory. And then you have the modulator that takes your bits and map, and according to these bits changes the properties of the carrier, which can be sinusoidal, rect, whatever carrier you want to use. How do you use a carrier that carries your information? You use a carrier that can propagate through the medium you want to communicate over it. For example, if it's wireless, the best carrier to use is a sinusoidal or sinusoidal with a sine or cosine. And you need to determine its frequency properly. Why? Because frequency is responsible for how long you can communicate. Yes? In the previous lecture when we gave the example of 100 megahertz and 900 megahertz, we said which signal can go farther, 100 or 900 megahertz? 100 can go farther. The coverage of 100 is more than the coverage of 900 megahertz. But why do we use 900 in our phones? We don't use 100. Because of the antenna. Yes, the antenna is lambda over 4. When you calculate the frequency is 900 and calculate what's lambda multiplied by the frequency equals c, which is the speed of light, then in this case you will find that lambda is, if the signal frequency is 900 megahertz, then lambda is equal to 32.8 centimeter. What's the antenna size? Is lambda over 4. 32 divided by 4, 8 centimeter. 8 centimeter, you can put them in your phone. But if you use 100, it will be, the wavelength will be 3 meter. 3 meter over 4, still you have 75 centimeter. 75 centimeter, you cannot put them in your phone. We gave this example last time. So, examples of communication channel. Communication systems convert information into a format appropriate for the transmission medium. This is what we have just said. But some channels convey electromagnetic waves, whereas some other channels convey different things than the mechanical waves. Example of the electromagnetic waves: radio, optical fiber, laser, and laser line of sight. Laser line of sight, this is the communication they use to communicate with the satellites on the air and on Moon, on Mars. Imagine they reach Mars. They can communicate with laser, like very tiny beam, like you cannot even sometimes see it in your eye, and from air reaches Mars. Imagine, carries data from the Earth to Mars and from Mars to Earth. Other channels use sound, smell, pressure, chemical reaction, smell like ants, chemical reaction, neurons, dance like bees. So this is different kind of medium that are used to communicate things. Analog communication systems basically convert analog signal into modulated signals ready for transmission over the air, while digital communication systems convert information in the form of bits into binary digital signals. So digital takes bits and convert them to digital signals that are ready for transmission. Analog takes analog signal and modulate them into signals ready for transmission over the air. Physical channels have constraints on what kinds of signals can be transmitted. For example, radio uses electromagnetic waves at various frequencies. Like the cellular phones, the wireless cellular networks uses the following frequencies for sending your data. Wi-Fi, which frequency Wi-Fi uses? 2.4 gigahertz and 5 gigahertz. 3G, which frequency uses? 2.4, 2.1, 2.4 unlicensed, free, everybody can use it, but 2.1 is licensed. You have to buy it from the government. So 2.1, 3.6, LTE uses 3.6, sometimes 2.1, 2.6, and 900. So these are the frequencies that are used by your cellular phone to take your data and communicate with it. And Wi-Fi uses 2.4 and 5 gig. There is also Y-gig, yes? We have GSM, UMTS, and LTE, and after that 5G. Yes, each one has different types of frequencies that it used to communicate over. And in Wi-Fi, we have Wi-Fi, which is A, G, N, H, yes, different types. Each type has different data rate, different frequencies. And we have Y-gig. Anybody knows Y-gig? Y-gig. The carrier frequency 60 gigahertz. The data rate 10 gigabit per second. And we have Li-Fi. So we have Wi-Fi, we have Li-Fi, we have Y-gig. What's Li-Fi? Li-Fi. Didn't you hear of Li-Fi? You know Wi-Fi. Li-Fi, don't you know it? Li-Fi, you take data from the light. The light is the access point. For example, now turn off the light, turn on the light. The light, no, when you turn it, when you turn on the light, yes, here, as if you turn on the access point. And this starts providing you with internet. The light. From the light you get your internet. You don't need access point. And your signal cannot go out of home, cannot go out of the room even. Just limited within the area. So you are secure. Nobody can get your data, listen to it and this. And this can provide you with 1 to 10 gigabit per second. And from where you can get it, you use the light, you use the light for illumination, for lighting your room. You can keep it. And for internet access. Okay, you can. So it's such an amazing technology that was built by communication engineers. Very clever technology. It's not like you use another thing for the internet. You use what's already available to provide internet. So you can, when you go home, you can maybe read a little bit about it. Y-gig, what's Y-gig, Wi-Fi, Li-Fi, the differences between them. These are new things you didn't know about before. So even your phone can communicate with Li-Fi. They have chips they can install and this and light, and then you can get your information. So wired links may require DC balance codes. Now these points are examples on cases where you need to use a specific modulation in order to send your data over certain mediums. Because the medium restricts you and tells you which modulation you will need to use so that you meet the requirements. Otherwise, it won't work well. For example, if you are communicating over a wired links, you need a modulation that achieves DC balanced. DC balanced means the DC value, they don't accumulate over each other. Because let's say you modulate the first one as +5, and the second one, another +5 becomes 10, and another third one becomes 15. So your voltage is becoming extremely high, and it becomes very dangerous. To avoid this, you use a modulation that kinds of achieve balance between the DC components, so you don't have such problems. We call this voltage buildup. Fiber optic channels use another type of modulation, we call it 4B5B, to accommodate time varying attenuation. In fiber, we have time varying. The channel changes within the duration of your symbol. Within the duration of your message, the channel changes. And this will affect your data. You cannot recognize it easily at the receiver. To avoid this problem, what do? You use a modulation scheme that's suitable to solve this problem. For CD, DVD media, CD, the one we require minimum spot size, but position can be more precise. So, as you can see, based on the application, based on the media, you decide which modulation you will use. For example, in the test or midterm or whatever exam, we can tell you, you have the following applications. You have Internet of Things for home, Internet of Things for agriculture, for tracking, for augmented reality, for virtual reality. And we give you 3 different modulations, like BBSK, ASK, single sideband, analog, digital. And we tell you which modulation is most suitable for this application. So basically, from the application, you know its requirements, and which modulation can meet these requirements, you map them. This is one of the tasks that communication engineer needs to be able to figure out. The process of creating a signal suitable for a transmission is called modulation. Basically, we defined it many times, and we all know now that your data as is not ready to be transmitted over the air. And modulation, what modulation does basically, it just prepares your data in a way that's suitable to be transmitted over the air. Your computer, for example, produces zeros and ones. Can you send zeros and ones as they are through the channel? Through wireless? You cannot 0 and 1. How can you send 0 and 1? 0 and 1. In software, when you write a code, it gives you the output zeros and ones. How can you send zeros and ones through a wireless medium? You can send them within the computer, in the application, store them. But now you are on a physical medium, wireless. How do you send them? Now you need modulation. Modulation prepares your data in a form that's suitable to be transmitted over the channel. Give me one example, one simple example of modulation that can send your data bits, zeros and ones. Sinusoidal signal. I tell, the sinusoidal signal can propagate through the air. Yes, sinusoidal signal. It can when your antenna gets excited by an electrical signal, current distribution on a form of sine or what, electromagnetic signal gets produced. Everybody knows this from physics. Yes, if you have a wire, yes, and electrical signal current passes through the wire, what happens? Produces electromagnetic signal around it. Yes? And this is basically what you have in the communication block diagram. You have electrical signal until you reach the antenna. The electrical signal can pass through the electrical wires, can pass through the electrical components, but when you reach the antenna, what happens? The antenna converts the electrical signal into electromagnetic signal. Because electric signal, you cannot send it over the air, for example, or over any medium, can you? Have you ever? Then why don't they transfer the power to us wirelessly? Yes, the power, the plugs, the electricity we get from here. Have you ever seen it traveling wirelessly? Always with cables, electrical cables. So basically, once it's electromagnetic signal at certain frequency can propagate through the air. So what modulation does basically changes the amplitude of this electromagnetic signal based on the data bits, zeros and ones. So the electromagnetic signal already easily can propagate and can walk through air. Yes? So all what you need is, since you cannot send the data bits directly through the air, you just change the properties. What do I mean by the properties? The amplitude of the sign, the phase of the sign, the frequency of the sign. According to what? According to the data bits, zeros and ones. So now give me modulation. Give me one modulation that can solve this problem. Let's say amplitude modulation, basic amplitude modulation. When 0 comes, make the amplitude of this electromagnetic signal low. When 1 comes, make it high. Yes? Simple as is. The receiver then takes the electromagnetic signal. If it is low, this means that the transmitter sent 0. If it is high, this means the transmitter sent 1. It's as simple as this. But very important to understand why. Why do we need electromagnetic signal? Why cannot we transmit electrical signal? Why cannot we transmit the bits directly through the channel? Yes? You get all this information. This is the example. This is the sinusoidal signal that I use for as a carrier to carry my data for producing the electromagnetic signal. And this is my signal, the message that I want to transmit. So basically, the amplitude modulation, you change the amplitude of the carrier, this one, the carrier, based on the incoming message signal. So the signal you transmit over the air becomes like this. The amplitude modulated one, the third one. You are with me? You have, this is your message. This is the one you want to transmit. This is what you produce. And this is your carrier. Why the carrier always has high frequency? Exactly, we don't want other people to listen, and we want to use practical antennas, and we want it to reach farther distances. So here, as you can see, the carrier shape changed based on the shape of the message. So basically, when you get this, the amplitude, the envelope of this signal, you get the message. How do you do that mathematically? How do you do that mathematically? You just multiply them with each other. You multiply the signal with the carrier. You get this. This is amplitude modulation. What about frequency modulation? Amplitude means you change the amplitude of the carrier based on the message. Frequency modulation, you change the frequency of the carrier, high or low, based on the message signal. For example, when you have high amplitude, when you have high signal amplitude, message signal amplitude, you choose, for example, low frequency. Low frequency means the oscillations are far from each other. The durations of the oscillation are not very close. For example, this duration here, this one, this is high frequency. The one before it is low frequency here. Why? Because here you complete the cycle within a duration that's larger than this. So the less time you need to complete one cycle means the frequency is higher. For example, if a signal completes full cycle within 1 second and another signal within 2 seconds, which one has frequency higher than the 1 second higher? Because in 2 seconds you would have completed 2 cycles. So you are faster. Frequency is higher. You understood this concept, very important. Now, analog signal versus digital system. Analog signal, like x of t versus time, you have continuous values. At any point of time, you have value in the power domain or amplitude domain. Values varies continuously. It's not, you can have infinity number of values between any 2 points. Digital signals value limited to a finite set. For example, you have either this value or this or this or this. Only 4 values. Your function can take only 4 values. Value limited to a finite set. Digital systems are more robust to noise errors. That's why we prefer to use them usually. Example of a binary system is given as shown in this figure. You have your computer generates zeros and ones, zeros and ones, zeros and ones, and to convey these zeros and ones, you produce electrical signal in a form of rect. When 0 comes, the rect is low. When 1 comes, the rect is up. So down, up, down, down, up, down. Yes? At the end of the day, at the interface, at the card interface, yes? Everybody, have you opened the computer? Want to fix it and this? You have the network card, yes? The Ethernet card. This is the Ethernet card or network card. Everybody knows what I'm talking about. Have you ever seen the motherboard of a computer? Motherboard of a computer inside the computer. You didn't see it? Everybody has computers and sometimes you need to fix it or repair it. In the card, this network card, or we call it Ethernet card, or we call it sometimes wireless interface card. This is, when you go there, this now, the data now is signals, electrical signals at the output of it. Doesn't know bits. I mean, how can you transmit bits over this? At that point, you start using this. If the input to that card, something in a form of bits, yes? At the MAC layer, just above the physical layer, you have bits. You convert the bits into signals like this. If 0 comes, the voltage is low. If 1 comes, the voltage is high. Low, high, playing with the electrical signal, and you send it. You send the electrical signal to another computer, which is in the same lab maybe. The other computer wireless interface or Ethernet card start reading the signal, the electrical signal. Checks if it is low, 0. If it is high, the amplitude 1. And then reconstruct the bits and start mapping the bits to the other layers, MAC, network, transport, application, until it reaches your application and start seeing the message, for example. So the process of converting your signal from analog to digital, we call it analog to digital conversion. And to do that, we need to use sampling and quantization. Basically, sampling, we will go through this in details in the future, but to give you an idea about how this works. Sampling is responsible for dividing your signal, sampling your signal in time. Quantization, dividing your signal in amplitude. So basically, you divide your signal in the 2 dimension, time and amplitude. The division of your signal in time depends on the sampling frequency, on the frequency of the signal. The higher the frequency, the shorter the spacing between these samples. And the amplitude, the number of values on the y-axis, depends totally on the quality of your signal. So if you want your signal to be of high quality, you must reduce the spacing between the vertical lines, the horizontal lines that divides the y-axis. And by doing so, you get points. And you convert these points into number, bits, zeros or ones, ones or zeros. And then you convert these bits, carry them via the electrical signal like this one. So this is how, for example, you can convert your speech signal or analog signal into electrical signal that's suitable to be transmitted over Ethernet, over the internet, over the wireless. Usually this is very important topic that I always ask about it. And whenever you go for an interview field related to communication, they will always ask you about it. So you must know, why do we use sampling? What are the parameters that affect it? Why do we use quantization? What are the parameters that affect it? And how to do that? How to do that, we will discuss it in the coming lectures. We will give practical examples with number and solve them exactly. And in the exam, you will do the same. Sampling, usually sample times are uniformly spaced. What does this mean? The spacing between these samples are equal. All of them are equal. The spacing between this point and this point is exactly the same as between this point and this point. And it's the same as between this point and this point. Higher frequencies content requires faster sampling. I just said this. If the frequency has if the signal has higher frequency, then the sampling needs to be faster to capture the details of the signal. Quantization levels are usually uniformly spaced. These are the quantization level. The spacing between them is uniform, is fixed, is the same. However, sometimes we use different spacing based on the fluctuations of the signals. In a digital communication system, after you convert your analog signal into digital and you have zeros and ones and you want to transmit them over the channel, you get a signal in a digital format like this. If 0 comes, then it's minus. If 1 comes, then it's plus. So this is the signal, binary signal input to the channel. This is the signal you transmit over your Ethernet cable, let's say. Yes, or this is the signal you transmit to your USB when you put your USB in your computer. Now, this, when it reaches the place where it needs to be decoded, it gets affected by noise. It gets affected by the channel medium. This shape B figure shows you the effect of the channel on your signal after you transmit it over the channel. And C here represents the effect of the noise on your data signal. And this D represents the signal after the receiver detects it and it tries to decode it. So as you can see, although the channel changed the shape of my signal, although the noise changed the shape of my signal, but I can still reconstruct the transmitted bits perfectly. Which is nice, this is the goal, to be able to transmit your data over a wireless medium reliably, without errors. And this is something that's amazing. We always want to be able to do that. So basically, how do you do that? You at the receiver, you receive this signal, C. How do you get this signal? You put threshold like this, line. If the signal is above this line, then it's perfect rect, perfect positive rect. If it is below, then it's perfect negative rect. This is the mapping you use at the receiver. And then you get this nice shape signal. And what do you do then? You come here, this is low, this is negative, then 0, this is positive, 1, negative 0, and then positive 1 1, negative 0 0 0, and then positive 1 0. You get your data bits, and then you convert your data bits to the message or text or image or video. As you can see, we are at the edge where we deal with the channel, the communication. That's why communication and computer engineering are complement to each other. They are side by side, supporting each other. If you want to understand the whole communication principle, you need to know computer engineering And if the computer engineer as well needs to understand the communication part. If you don't understand both, you will always lack some knowledge. You don't have solid interpretation for all the phenomena that happens during the communication from point A to point P. So basically, the guy who knows computer and microcontrollers and also knows the communication and the medium and wireless can create amazing applications that can be very useful. Channel errors. If there is too much channel distortion or noise, I told you this signal is after noise, after distortion. But what if there is too much channel distortion? Receiver may make a mistake. Let's say here too much noise, that it became negative. Then can you detect it correctly? No, you will detect it wrongly. The receiver can make a mistake and the regenerated signal will be incorrect because instead of detecting 1, you are detecting 0. And then your message will not be clear, it will be wrong. Channel, in this case, what do? We use channel coding in order to detect that there is an error and try to correct it. So this is what channel coding does. Detect if there is any error and try to correct it back. So this is your original data signal that you transmit over the channel. This is after being corrupted by noise, and this is what you get at the receiver side after using thresholding. Now I told you about sampling and quantization, and we said we sample the signal in time and quantize it in amplitude, and then we have points, these points. These points at the end of the day, I need to map them to bits so that I get a digital signal composed of zeros and ones that can be converted to electrical signals of up and down, down and up. Okay, what do now? I need to be able to convert these dots, these points, to digital binary signal. I need to use mapping table. This is the mapping table that I use. From 0000 to 1111 if the number of levels that I'm using are 16. So basically, where do you put? You put here 000. You say this level, I map it to 000. Any point in the signal that's close to this level, I map it to 000. And then after that, 1000, and then 0100. So basically, these points, you map them to here. You get the signal on the y-axis. And at the y-axis, instead of putting values, instead of putting numbers, you are putting bits. That represents the values. And when you want to represent your data, instead of getting the values of these points, you just get the bits of these points and attach them, concatenate them beside each other. And then you have binary signal ready to be transmitted or stored. So basically use this mapping table, and look here, when 000, all of them are negative. When 0001, then all of them are negative except last one is positive. Basically, this is the electrical signal you generate for different codes, for different binary codes. To communicate sampled value, we send a sequence of bits that represent the quantized value, as I just mentioned. For 16 quantization level, when we have 16 level on the y-axis, how many bits per level I need? 2 to power how much I get 16? 4. I need 4 bits, that's why I use here 4 bits to represent the 16 level. BCM can use binary representation of value. You represent your value in binary, and computer understands binary, and you are done. You can deal with your signal in the digital domain now. Public switching telephone network, Ethernet, many communication systems are built based on that. Used with different levels, of course. Now, I have transmitted my signal reached to the receiver side, and I want to get my data back. But my signal is corrupted by noise. is not perfect. How do I measure the performance? I use certain performance metrics to measure how good, how reliable my signal is. One of the metrics we use to evaluate the reliability of your system, you design a system, you design a system, you designed a system, you over there designed a communication system, and as a company, all of you engineers, you are submitting your systems to me. And I want to check, I want to report to the manager, to the owner of the company, tell him which system is the best. He is asking me which system among your systems is the best to be used in the company. I tell him, okay, let's evaluate these guys' designs. I come first to your design and check. Tell you, let's operate your system. You tell me, okay, let's put a message signal of M of T as an input to the system. Okay, and then I receive M hat of T. M hat of T represents the received signal at the receiver. So M of T is the message you transmit at the transmitter. It's not affected by noise, not affected by channel. M hat of T is the message, is the signal you receive at the receiver after passing through the channel and noise. So what I do, I just subtract what I receive from what you transmitted, take the amplitude value, square it, and integrate it over time to get the energy of different signal. I get for you, for your signal, I get 0.5. Remember this value, put it aside. I come to your design, you designed a very amazing system, yes you, and when I calculated these things, I found that the value is 0.5, 0.4, not 0.5, 0.4. Yes? Which one is good? Which one is better so far? The one that gives 0.5 or 0.4, which one? 0.4. 0.4 is better. Why? Because the difference is smaller. The difference is smaller means the received signal is much closer to what you transmitted. It's easier for me to detect it. But there is also another guy who designed a system, very perfect system, and gave me 0. This means the M hat of T is exactly the same as the transmitted one. What an amazing system. You cannot do much better than this. Of course I will go with that. But he will tell me, okay, but there is a catch. My system, to achieve that, it uses so many sophisticated circuits and complex encoding, encryption to protect your data, because there is nothing for free. There is no free lunch. You provide such an amazing, highly reliable system, you must be paying some prices. And the price you pay for that is the sophisticated circuit design you have built to achieve that performance. So this is how we measure the performance. This is how you, as an engineer, can evaluate the capabilities and reliability of different communication systems. Now, we also use this metric. We call it energy of difference signal. Why it's energy? I told you, because it's amplitude, you square it, becomes power. You integrate it over the time, becomes energy. Everybody knows this from circuit theory 1 and circuit theory 2, yes? Metrics are data. There is another metric, which is error probability. Error probability is the probability that what I receive is not equal to what I transmitted. So B hat is what I received, the bit I received, and B is the bit I transmitted. What's the probability from random analysis and the probability course? What's the probability that these are not matching with each other? I sent 1,000 bits. One bit was received in error, and the remaining ones were received successfully. What's the probability of error in this case? 1 over 100, over 100 or 1000, I said. 1 over 100 bits, because I transmitted 100 bits. How many bits in error? 1. 1 over 100, 1% error probability you have in your system. Can you use this for a critical Internet of Things as an engineer? If your application is very sensitive, very critical, you need to have 1 over 1 million. 1 error in 1 million bit. So this 1 over 100 is not good. So it depends on the application. But if you are using it for voice communication, it's fine, maybe. It depends. So you start thinking, you start deciding as an engineer, when you understand things and connect the dots with each other, you become wise engineer who knows the why, not only the how. Not only how to derive it, how to find the answer, but why? Because the customer doesn't understand technical details on this. You need to explain it to him in a very simple lowman language where he can understand you easily, and you can only understand this, you can only explain this easily if you understand things and the why behind them. Without noise, we never experience bit errors. True or false? Question in the exams. Without noise, we never experience bit errors. True or false? That's true. If we don't have noise, we don't have interference, we don't have anything, then we don't have communication. You will not be studying communication course. It will not be a course in electrical engineering if we don't have noise, if we don't have interference. If what you generate at the transmitter, you can just send it and it will be received all the time correctly, then you don't need this science. So it's because of noise, because of interference, because of the impairments of the channel and difficulties we face, we have communication, and we need to design systems that are reliable. With noise, the probability of error depends on the signal power, how high the amplitude of your signal is, the noise power, how low or high the noise power, data rate, how fast you communicate and send your signal, and channel characteristics. Data rate limits. Everybody from time to time hears that my internet provider, Turk Telecom, gave me my home internet of 100 megabit per second speed. What does this mean? As a customer, you know that it's better than 10, and 1 giga is better than 100. Yes? But what's this data rate? This is the amount of information that your channel can support. What's the channel? The medium, the cable. Yes? You get from Turk Telecom or any that reaches to your home. The maximum data rate that your cable can support, while considering the noise power and signal power and distortion. So when you want to upgrade from 100 mega to 1 giga, what does the provider gives you? Gives you more cables. Like in the center, in the switching center, assigns to you another cable, for example, or increases the power so that it gives more data rate. Because data rate basically is related to the Shannon capacity equation, which is equal to, for additive wide Gaussian noise, when you don't have wireless fading, just like think of it like communication between over wires or communication between satellite and the ground station, satellite and TV. In this case, you only have additive wide Gaussian noise effect. So what's the channel capacity for this system is half of the bandwidth multiplied by log 1 plus the signal to noise ratio. This equation that was obtained and derived by Shannon in 1949, 48 even, teaches us that the maximum data rate you can transmit without errors is limited by the bandwidth of your medium, the cable, and the signal to noise ratio. Signal to noise ratio is equal to the power of your signal over the power of your noise. The higher this ratio is, the better your signal is, the better your data rate is. So now you know what, if your data rate is low, you know the reason. Either the bandwidth is low, or the noise is high, or the power is high or low. Basically, you need to increase this, increase the power, reduce this, increase the B to get high data rates. The Shannon capacity is the maximum possible data rate for a system with noise and distortion. Maximum rate can be approached with error probability approaching 0. So basically, Shannon capacity is the maximum data rate you can achieve while having 0 error probability. For additive white Gaussian noise, we have this equation. You need to understand this equation very well and understand the relationship between capacity, power of your signal, power of your noise, and bandwidth. From this equation, I can bring many questions. For example, I tell you true or false. As we increase the noise power, the data rate decreases. True or false? Everybody raise your hand. If it is true, raise your hand. Should I repeat the question one more time? Yes? Should I repeat it? That I say that I can bring many questions on this formula on the exam. For example, I can say, as we decrease the noise power, the data rate will increase. True or false? As we decrease this, the noise power N, the data rate, which is C, will increase. True or false? If it is true, raise your hand. I will consider the ones who don't raise that they said false. Raise your hand. Be confident. If you don't know, just say I don't know. I already explained it. I was explaining to you. So again, the question says if the noise power is reduced, which is N in this equation, the data rate increases. True or false? True or false? Raise your hand. Up or down? Up or down? So here we have all up. Here all up. Oh, you don't know. Okay, you are frank. You don't know. Basically, most of you are right. True. If we decrease this factor from math, yes, everybody with me, but really not by guessing, we are not guessing here. It should be based on logic, yes. You have here the denominator, noise. When you decrease this, what happens to this value? Yes, everybody with us? This is the why you answered it true. When you decrease this, the whole value increases here. For example, 5 over 1 is 5, but 5 over 0.5, 10. When you increased, then log of this increased number even more. And more multiplied by the bandwidth is even more. This means that the data rate increases. The theoretical result doesn't tell how to design real systems, but it gives you guidance of how much you can achieve. And Shannon obtained capacity equal to 32 kilobit per second for telephone channels, and the bandwidth is measured by 3700 hertz minus 300 hertz. Why minus 300 hertz? Because your speech signal starts from 300 frequency, not 0. You cannot reach 0 usually. from 300 to, that's why the bandwidth of your voice speech signal is 3400 hertz or 3.4 kilohertz. And modern modems achieve higher rates by using more bandwidth and complex receiver structures and advanced signal processing techniques. So with this, we finish our lecture and meet you in the next lecture. Thank you very much for your attention.